This video gives a detailed architectural overview of our tree cover delineation framework from 1 meter very high resolution NAIP imagery data using a deep learning algorithm. Satellite imagery exhibits a multitude of land cover classes, as you can see from the images here. A high variability in land cover types makes any classification problem challenging for satellite imagery datasets. The quality of data is affected by conditions in data acquisition, data preprocessing, and filtering. Class cognition is tough even for human experts owing to high variability in the land cover types as well as variations in atmospheric and lighting conditions. Satellite imagery datasets are typically of the order of terabytes. The NAIP dataset has 65 terabytes of images with 330,000 scenes. Each image tile is typically around 7,000 by 7,000 pixels. So this big data problem calls for a predictive on-demand analytic solution. So we build our framework on top of a high-performance computing architecture for providing intelligent insights on the fly. Now, we provide a detailed overview of the system architecture. First, images from the NAIP dataset are split and fed in parallel to the cores of the high-performance computing platform. The three HPC modules perform segmentation, feature extraction, and classification. Finally, the results from the segmentation module and the classification module are combined using a conditional random field, which in turn generates the final output image. The output is saved into the NAIP dataset. The training dataset is updated at regular intervals to improve the accuracy of the classifier. Segmentation is done using the statistical region merging algorithm. Under-segmentation creates interclass overlaps, so we create an over-segmented image. Here's a list of some of the features extracted by our framework. Once extracted, the features are fed into a deep belief network for classification. The weights of the DBN can then be used to initialize the weights of a neural network to produce the final classified image. In a DBN, each layer is trained using a restricted Boltzmann machine, as you can see in this figure. Finally, a conditional random field performs structured prediction to combine the labels generated by the SRM algorithm and the DBN-based classifier. We produced promising results over the state of California, having achieved detection rates higher than any other algorithm on such a high-resolution dataset. As you can see from the table, we produced average true positive rates of over 80% for the state of California. Now, I would like to walk you through some sample images from the dataset and the results we achieved using our high-performance deep learning framework. As you can see, the left panel shows a sample tile from the NAIP dataset which measures around 7,500 pixels in height and 6,000 pixels in width. In the output tile, The white pixels denote the tree cover areas while black pixels denote non-vegetated areas. The image that you see now contains the entire California mosaic of the output tree cover masks generated by our framework. The green pixels in the image show the tree cover areas, while the white pixels denote non-vegetated areas. I would like to zoom in to provide a better view of the image and the kind of resolution that it shows. In order to give an insight on the total area covered, here's an online link which covers the whole of California and shows the NAIP tiles that we processed using our framework. As you can see in the map, each small box represents a NAIP tile and the red dots indicate our validation samples on which we achieved an average accuracy greater than 80%, which is higher than any other existing algorithm. So that's it. Thank you.